Hello everyone, and welcome to Module 4, this video lecture for Chapter 29. We are basically done with the study of electrostatics and electricity, and now we begin with a new topic, which is the last topic of the semester, and that is the study of magnetism. There are 3 chapters on magnetism: Chapter 29, Chapter 30, and Chapter 31. The first one here is the magnetic field, and then Chapter 30 is magnetic induction, and then on Chapter 31 is the electromagnetic waves. These are basically the 3 last chapters. Some years when I teach this course, if I have time, I would cover AC circuit. But I don't think we will have the time to do that in this semester. Before I begin, I want to go back to the course, and I have been getting email messages from students saying, when is the midterm exam? And to my surprise, since day 1, I have made announcements in class about the course schedule, which is under, you see it located here under Module 0. Module 0 have 3 items here, and one of them is the course schedule. If you click on that, you will see the schedule right there, and it basically tells you it's divided into weeks or modules, and we are right now in Chapter 29, and the due date for Chapter 29 homework and quiz is on the 26th. I believe the quiz is on a Monday night, right? We changed that. But keep in mind that the midterm exam is going to be this coming week, okay? So the midterm exam number 2, is going to be, it's going to open up on a Friday, April 24th, and it will close on the 26th, which is a Sunday, and it's going to be over the chapters that we have not been tested on during midterm 1, okay? So it's going to be Chapter 26, 27, 28, and this present chapter. And then we still have 2 more chapters to go. Chapter 30, electromagnetic induction, and Chapter 31, electromagnetic waves. And these are basically 1-week modules. And then on the last week of this, well, that's basically it, Module 7, which is the last week of the semester. And then after that, we will have the final exam. And I am not yet sure when it's going to be held. We're just going to have it online, of course. But I haven't decided what the date is going to be. But it's going to be something like, going to open up on a Friday, close on a Sunday. And it's just going to be, like I said, the final exam is a cumulative, all the chapters that you have studied, but it's going to be selective. I will tell you which chapters, which section that you need to study for it, okay? We'll talk more about that later when we are close to Module 7 or Module 6, okay? So keep in mind the exam, we have midterm exam on the 24th. Let me show you the calendar very quickly. I am recording this video on Sunday, but of course we start on the 20th. So the exam is going to open up on a Friday, the 24th, and it's going to close on the 26th. I haven't done it yet, but basically that's so expect that. Make sure that you take the exam within those 3 days, okay? All right. Back to the chapter. The chapter, the magnetic field, is a very large chapter. If I had the time, I would turn it into 2-week module, but that means I have to sacrifice one of the chapters that you need to study, so I'm not going to do that. So we have to squeeze in, try to cover all these materials within 1 chapter. There are really a lot of material in this chapter. So my advice to you is to pause this video and then go back to the book and read the whole chapter. This is really the best way to do it, because it's really difficult for me to cover every single thing mentioned in the chapter within a 1 hour, 1.5 hour span, okay? So what I'm going to be doing, I'm going to tell you what the topics that you need to learn in the chapter, and then I'm going to be doing one or two examples on each topic, okay? So let me go back to the note here. The topics that is going to be, let me just list them for you. The first topic is the Biot-Savart Law, which basically those topics that I'm going to be covering today. So Biot-Savart Law, that's the first topic. And then we're going to be covering the formula F equals, F as a vector, F equals Q V cross B. And then we're going to be covering the equivalent formula F equals I L cross B, and Amperes Law, the line integral of B dl dot dl is equal to mu naught I, and which result into that the magnetic field is equal to mu naught I over 2 pi r. More on it in a minute. And then the last formula is the force between two current carrying wires, and that would be the force between them is equal to mu naught over 2 pi I1 I2 over d, the distance between them, times L, which is the length of the wire. Okay, these are the topics that I'm going to be covering today, and I'll try to cover them, you know, within an hour, maybe an hour and a half. I'm not sure how that's going to go, this video is going to go, but I'll keep going. All right. We begin with the Biot-Savart Law. And Biot-Savart Law has two versions, one for the current and one for the charge. The one I'm going to be covering is only for the charge. Let me tell you which equation. Maybe I should go to the book. Let me show you. It should be here. Nope, next page. Section 3, actually. Yeah, section 3. This is the formula that we'll be using right here, okay? I'm going to present the vector version of it. I don't know, that's a vector, there's no vectors here, that's funny. But anyway, this is the scalar version of it, but I'm going to be presenting the vector version. And this is a very good diagram. I didn't notice it, so I'm going to be using this diagram in a minute. So let's start on it. So first, the Biot-Savart Law. And by the way, there are plenty of videos on the YouTube by, you know, people who want to explain stuff like that. There's really tons of them. And I would advise you, just go to the YouTube and type something like Biot-Savart Law or whatever topic. And you'll find tons of videos of people just explaining them. And a lot of them are pretty decent videos. You know, they're very, very good. So you can learn a lot from them. Anyway, so basically what it says is the following. Any moving charge, okay, there is an associated with it a magnetic field. In other words, any moving charge generates a magnetic field, okay? For example, let's say I have a charge, say a positive charge, and it's moving with some velocity v. This is the charge q. Okay. As it is moving, okay, it must be moving. If it's not moving, there is no. Well, let me back up a little bit. If I have a charge positive and it's an electrostatic charge, which means it's not moving, the only field associated with it is just the electric field, the one we know. Okay, so there is an electric field coming out of it like that. E equals KQ over R squared. Okay. That's basically what you get. Now, when you take this charge and actually put it in motion, just like this one here, this one right here, okay, what will happen as it is moving, beside the electric field on it, okay, there will be a magnetic field associated with it, okay, and the magnetic field symbol is B, okay? And the unit of B, again, I want to be, so the unit of B, the magnetic field, is the Tesla. Okay? And Tesla, just like the Coulomb, is a very, very large unit. Okay? So let me say that. B is the Tesla, big T, and it's a very large unit. So don't expect that when you do a calculation to get something like 500 Tesla or 1,000 Tesla. You're not going to get that, okay? In a typical, say, lab, physics lab, say Argonne National Lab or Sandia or whatever, you know, a typical would be something like in the range of 5 Tesla, 4 Tesla, maybe 10 or 12 Tesla, but it's not going to be more than that, okay? Typically expected to be in the range of 0.1 Tesla, 1 Tesla, 3 Tesla, and so on. Those are basically and that 3 Tesla is extremely strong magnetic field. Keep that in mind, okay? Very, very, very strong, 3 or 4 Tesla. So 10 and 12 is just astronomical, okay? But don't expect 500 or 1,000 Tesla, because Tesla by its own nature is a very large unit. Another unit that is used is called the Gauss. And 10,000 Gauss, 10,000 G, is 1 Tesla. This is used a lot in the medical profession. For example, the NMR machine or something like that. I think you will find the unit to be written in Gauss. But Gauss is used, but this is a CGS system of unit, and the Tesla is the MKS. Both SI, but the one that is more popular for physics and astronomy, the SI system, is the Tesla rather than the Gauss. But be familiar with them. So 10 to the 4th is equal to 1 Tesla. 10 to the 4th Gauss, that is equal to 1 Tesla. Anyway, so back to our discussion here. So I have a charge Q moving with a velocity V, any velocity, whether it's high speed or low speed. As long as it's moving, there will be a magnetic field generated around it like that. A magnetic field always go in a circular way, okay? They don't go in a straight line way like in the electric field. They go in a circular way this way. They follow the right-hand rule for the cross product. But basically, that's how they look like as the charge is moving. So the charge is moving, and the magnetic field is going like that as the charge is moving there. You see what I'm saying? In addition to the electric field coming out of it in the radial direction, you got that? And so on. Okay, and there is a way to measure this, and to measure this magnetic field associated with the charge is what is known as the Biot-Savart Law. Let me write it down for you, and it's full of glory, and then we'll talk about it. So the magnetic field associated with that moving charge is equal to mu naught over 4 pi Q V cross R unit vector over R squared. Okay, this is the proper way of writing it. I don't know if your book uses this one. I know he has the scalar version of it. I'll talk about the scalar in a minute, but he probably doesn't have it, does he? Look at your book here. Easier to... No, he doesn't. Oh, there it is right here. It's equation 29.4. Let me go back to it. 29.4. 29.4. Sorry, it's taken a while. There it is right here. Okay, this is the formula that I have just written. This is the vectorial version of it, if you will. Okay, mu naught here is just like, you remember epsilon naught. Remember epsilon naught, which is the permittivity of free space. It's equal to what? 8.85 times 10 to the negative 12, whatever the units are. This one is called the permeability of free space. It's 4 pi times 10 to the negative 7. Okay? Make sure, look it up here. Mu naught. Sorry about that. I think it's correct. The book doesn't show it. They show it in a 1.26. But anyway, there it is. This is called the permeability of free space. It's always associated with the magnetic field. And this is called the permittivity of free space. What's interesting about those two constants, if you multiply them, if you use this formula, 1 over the square root of mu naught epsilon naught, you know what you get? You get exactly the speed of light. Isn't that weird? Okay, but we're going to cover this formula when we go over the last chapter, chapter 31. But anyway, that's basically what it is, okay? So what does that mean? What's the meaning of this formula? What's the meaning of it? Let me draw you, well, here's the diagram. I mean, the best thing is to show you this diagram, which is kind of hard for me to draw. It's right here. Okay, let me make it bigger. Okay, so as you can see here, there is a charge Q, okay, and it's moving with a velocity, this green vector, V, okay? And let's assume, and I told you, as the charge is moving, there is, think of it like a spiral field around it like that as it is moving. You get that? Okay, so let's assume that I'm interested in finding the intensity of the magnetic field, let's say at this point right here, okay? So first of all, you ask the question, how far is this point from the charge? Well, it's equal to R, okay? So the R is the distance, okay? The R is the distance. What is the formula? Here it is. This R right here is the distance, because I am interested in finding the intensity of the magnetic field at this point, and well, how far is it from the charge at that moment? Instantaneous distance is R, okay? And then you get this R, this distance R, well, there is a unit vector associated with it, okay? And that unit vector is this one, okay? R, the little hat here indicates it's a vector, but it's a unit vector, which means the magnitude is 1. You get that? So that's the meaning of it. So V cross the unit vector R divided by how far is it squared, okay? I mean, it's an inverse square law, as you can see. It's similar to the electric field, kind of, you know, more or less similar to electric field. But remember, magnetic field does not come out unless the charge is moving. This is the very important aspect of it. The charge have to be moving in order for the magnetic field to come out. So, all right. So if I want to get this magnetic field, I basically say that the magnetic field is equal to this constant, okay, mu naught over 4 pi, times the amount of charge, times how fast the charge is moving, crossed with the unit vector over the distance squared. Let me simplify that a little bit better. If you remember from cross product, if I have, let's say, A cross B, okay, the magnitude of that is equivalent to A B sine theta, correct? What that means, let's say here is a plane. We go back to calculus here. Let's say you have a plane, and let's say you get two vectors, vector A right here, and then vector B like that, okay? Let's say I want to get B cross A. Okay, so B cross A, that is the angle between them, right? Theta. So B cross A is going to give you a vector that is perpendicular to the plane of the two vectors, which is basically this vector. This is A cross B, B cross A, excuse me. Okay, and well, let's call it C, for example. Okay, and that's the angle between them. So another way of, this is how it looks like on the left-hand side of the equation. Okay, now the right-hand side of the equation here, which is a scalar form, it basically says the magnitude of A times the magnitude of B sine the angle between them, okay? So there are two equivalent statements here. You can either use the cross product, or you can use the, not scalar product, but AB sine theta, got it? So now, with this in mind, with this formula in mind, I can come back here and I write the magnetic field B without writing the vector on top of it, to be equal to mu naught over 4 pi Q. Well, I have two vectors here, V and R, so I'm going to use this this version of it, which is the right-hand side, so it becomes V, which is the magnitude of V vector, times the magnitude of R unit vector. Well, this is just 1, right? Because it's a unit vector, so we don't even write it, times the sine of the angle between them over R squared, okay? And that's the scalar version of the magnitude of the magnitude of the magnetic field. You got it? So, and that's basically what that first formula that I showed you. Can I find it quickly? Formula 29.1, the first equation. There it is, right here. So you see that sign. That's the reason that is that sign, is because you take the right side of that vector equation. Got it? Okay. Let me do this example. This one is kind of a nice example, then I move to the next topic. This should give you an idea how to calculate the magnetic field associated with a moving charge using the Biot-Savart Law. This is a good example. Let's read it together. He says, a proton moves with velocity 10 to the 7 I, which means in the x direction. As it passes the origin, what is the magnetic field at the following positions? 1, 0, 0, 0, 1, 0, 1, 1, 0. Okay, I want to calculate that. Okay, let me show you how that works. So here is the picture. Okay, I'm going to draw it again. Let me move it as far as I can, but within the video. All right. If I can do it with my hand, it's always easier. All right, so I have here example 29.1. Okay, so here is the x and y. I'm going to try my best to draw it as nice as the one shown in the figure. Then I have this. Then I got that. Like this, okay? This is the x-axis. This is the z-axis. Ah, nice looking z. And this is the y-axis, okay? And then I have the positive charges right here, okay? There it is. And the particle is moving in the x direction. How do I know that? Well, it's given to me, right? He says, oop, what did I do? It says it's moving in there we go. So the velocity is equal to 10 to the 7 I, right? Meter per second. Okay. Now I want to find the magnetic field at the following points. Point 1, 0, 0. What is that point 1, 0, 0? 1, 0, 0. So the point basically, let me delete this V here. Oops, that's not what I meant, but here is the V. I'm going to make it short. Okay, so here is 1, 0, 0 right there. Okay, this is point 1. And then the other point is 0, 1, 0. What is that? 0, 1, 0. That's going to be right here. Right, that's point 2. And then the last point is 110. Okay, 110. Well, what is 110? 110 is going to be right there. Right here, point 3. Got it? Okay. Now, if I use the right-hand rule, and I urge you to learn the right-hand rule, the magnetic field direction is going to be like this for all of them. Going to be this way. I'm going to show you a video in a minute how to use the right-hand rule. This I'm going to call that B2, and of course B1 is here. Is that right? Like that. Got it so far? Okay, I want to calculate all of that. So how do we do it? Well, the Biot-Savart Law. Let's talk about B1. B1 is mu naught over 4 pi. It's a proton, so the charge is E, right? Remember, I'm using this formula. Let me go back. I'm using this formula right there, okay? Please write it down. Don't just sit back and watch me. Have a notebook with you and a pencil. I would urge you to write everything down, so I don't need to scroll back and forth. So this is the formula that we're going to be using, so please write it down. Pause the video, write it down, so you can work with me. And then you get, of course, to get the velocity, you get the sine theta. All right. So here it says EV sine theta over r squared. Well, let's calculate that. So mu naught, I'll come back to this mu naught of 4 pi in a sec. So E, okay, the velocity, well, we know what the velocity is, 10 to the 7. I don't need to put vectors anymore, the I here, because I'm replacing it with the scalar version, which is the sine, okay? Anyway, times the sine, the angle. Okay, so here's the velocity vector right here, right? and here is the R unit vector is right there. You see what I'm saying? So the angle between them is what? 0. So that's going to be sine the angle 0 over how far are they from each other? Well, it's just I mean, the distance here is, what is it? 100, right? 100 in the millimeter. We're going to convert. So that's basically 10 to the negative. What is it? 10 to the negative. Let's just do it this way. 0.001 squared. And of course, this answer is 0. So in other words, there is no magnetic field along the line of motion, if you will. Okay? Along the line of motion here, there's no magnetic field. All right. I think hopefully some of you have predicted that already. All right. Let's do number B2. Oh, before I go on. So what is this equal to? Well, it's mu naught. Let me just do it on the side. Over 4 pi. Remember, mu naught is 4 pi times 10 to the negative 7 over 4 pi. So practically is really just 10 to the negative 7. You can just use that and that's it. Got it? All right, B2. B2, now we are working with this one. Can I use a red color? Probably easier for you. Or pink? Okay. So in this case, where you're working with this one here, so in this case, it's going to be mu naught over 4 pi E V sine what? Well, it is, here is V, right? That's V. And now the R is this way. Here's R. And the R unit vector is right there. So what's the angle between them? 90, correct? Over, how far is it from here to here? Well, again, it's the same as this number, 0.001 quantity squared. You see what I'm saying? And then you plug in the numbers. You do the calculation, please. So that's 10 to the negative 7 times the charge, which is 1.602 times 10 to the negative 19, times 10 to the 7 for the velocity. Sine 90 is 1, divided by that, 10 to the what? 10 to the 4, I think, negative 4 or something like that. Anyway, so we calculate that, and I'm just going to cheat the answer from the book. We get B2 to be equal to 1.6 times 10 to the negative 13 Tesla. There we go. You got it? You see how I did it with the Biot-Savart Law? Okay. Notice the magnetic field, how small it is. It's really, really, really tiny. Okay, it's almost negligible. Even though we said Tesla is a large unit, but this thing is really small anyway. Okay. So, but that's how you calculate this. Now we go to the next topic, the next charge. Let me use a different color. So we say, I never used purple. Let's try that. So now maybe I should delete some of that. It's too much clutter. There we go. That's not what I meant, but anyway. Okay, now what I'm going to do, I'm calculating this one here. So this is R right there. And that's the R unit vector. You see that? Okay, so the angle between them is right here. So that's 45 degrees, right? So in this case, B3 is going to be mu naught over 4 pi E V sine 45 divided by, well, how far is this from the, how far is 0.3 from the charge? Well, it is kind of the hypotenuse of a triangle. You agree with me on that? Here is that triangle right here. See that? So if this is 1 millimeter, this is 1, that's square root of 2. So 1.41 times 10 to the negative 3, quantity squared. Is that right? And then you do the calculation. I'm sure this stuff is easy for you, this part. So the answer would be 0.57, again, I'm just getting it from the book, times 10 to the negative 13 Tesla. You got it? There we go. And that's how you got it. Now, if you want it in vector form, well, this one is along the z-axis, so I can write it this way, k unit vector. Same thing here, k unit vector. And this is the 0, the null vector, but it's a k unit vector. Got it? Okay. All right, moving on to the next topic. I hope this should be good enough for you. Again, you're welcome, always welcome to you know, go to Ask the Professor and then post your question there. Tell me, hey, Dr. Project, give me, what's the answer for, or how do you solve problem number so-and-so? I'll be more than happy to help you with it. Okay, the next topic, which is, sorry, let me look at my notes. I know it is not, I don't use the order of the book. Oh, it's in my blue notebook. There it is. Okay, the second topic is this one, is that a charge moving in an external magnetic field. In other words, not, remember the previous topic here, we generated, a charge moving, and it's generating that magnetic field, okay? And that magnetic field can be calculated by the Biot-Savart Law. In this case, however, we are talking about a charge. Say, here is a charge, and it's moving. We're not talking about how much magnetic field it's going to generate. No. It's moving into a magnetic field, an external magnetic field, okay? So how the charge is going to behave when it moves through the magnetic field, that's what we're asking, okay? And to do that, you have to use the right-hand rule to predict the force. So what I'm going to do now, I'm going to pause for a second. I'm going to have you watch this video, a little bit of it. I've already prepared it for you. I got it from the YouTube. I just kind of discovered it this morning. And I'll have you watch some. I'll just start it from the beginning. Sorry about that. This is really loud. Kind of killed my ears.
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 31. It's on the magnetic force. Imagine we have a charged particle, like a proton, moving through space. Since there's no force acting on it, no field acting on it, it's just going to keep going in that direction. But if we have a charged particle that's moving by a magnetic field, like it's rushing from the sun and it's coming by the Earth, and the Earth acts as a big magnet, what it's going to do is it's going to apply a force to that, and it's going to spiral into the planet, and it causes the northern lights. As these protons and electrons hit in our atmosphere, we're giving off ionization colors. And so as we move into magnetic forces, we really are moving into a third dimension. And so we have to have a way to deal with that. So if we have just 2 dimensions, it's easy to do that on a piece of paper, but how do you do it with 3 dimensions? A magnetic field, for example, coming at you or going away from you. The way I remember it is it's like an arrow. If an arrow is going through a hole, you're just going to see that point on the end. And so if you see concentric circles like that, or a bunch of them, that means the magnetic field is coming towards you.
Out
and
the
then
page.
the tail end of the arrow is going to look like that. And so if we see a plus sign or a X inside the circle, that means that it's going away from us. And that'll make sense.
In my, the way I think about it is, this one here is out of the page. You know, when you are looking at your page, out of the page. And this one is into the page. You got that? So here we have, you have y-axis, so that's up and down, and then you get the x-axis, which is right, left, and then into, out to is given by those 2. So the dot is out of the page, and the cross, I like cross, not a plus, and the cross is into the page. You got that? Okay.
Plus sign or X inside the circle, that means that it's going away from us. And that'll make sense when you see diagrams like this. So we've got a magnetic field you can see that's coming out at...
As you can see here, these dots indicate that the magnetic field is coming out of the page. You got that? So in other words, in the back, behind, let's say you're looking at it through your computer screen. So behind your computer screen, there is a north pole. And then out in front of the computer screen, there is a south pole, because magnetic field goes from north to south. So this magnetic field is coming out of the page. And then you got this charge right here is moving. Let's assume it's moving to the right. Now the question is, what's the direction of the force on the charge? Okay. In this case, you have to use the right-hand rule. And that's what he's going to show you. And then we'll stop the video. You can watch the rest of it later.
no magnetic force. But as it moves, it has a velocity vector. And if you're ever moving as a charged particle through a magnetic field, then you're going to have a force applied to you, and we call that the magnetic force, or F sub m. Now, things that you need to remember is that it's a perpendicular line between the magnetic force and the velocity, and it's also perpendicular between the magnetic force and the magnetic field. But the velocity vector and the magnetic field vector don't have to be perpendicular to each other.
Okay, hold on. Okay, so keep in mind you have three vectors here. You get the magnetic field, which is out of the page, and then you have the velocity, which is to the right, and then you have the force, which is, for this case, is down. I'm going to show you how that works. But we get those three. Those three are mutually perpendicular, okay? In other words, if one of them is not, you only take the perpendicular component. Okay, the way he said it's kind of ambiguous. He said some of them don't have to. Well, yes, they don't have to, but you always take the perpendicular component of it. So anyway, continue.
How do we calculate the magnetic force? Well, there are only three things that really deal with that. First one is going to be Q. That's going to be the charge of that particle. In this case, it would just be the elementary charge. We then have the velocity vector, or the speed of the particle, and then we're going to cross product that with the magnetic field. And what's a cross product? Well, these two vectors, when we magnetic force acting, you have to use the right-hand rule.
Okay, so this is the one you need to know.
And so it takes a second to get this figured out, but I'm going to hold my fingers out like this.
Remember, this is your right hand, not your left hand.
Pointed out. That's going to be the vector of the velocity. So in other words, where that charged particle is moving. I then have my middle finger moving at 90 degrees to that, and that's going to be the magnetic field. And then the force is going to be your thumb. And so you try to make these three dimensions with your finger, and you can solve really intense problems like this. You might look like an idiot as you're doing that, but it's worth it. And so let's say we have a charged particle that has no velocity and it's in this magnetic field. How big is our force going to be? Well, we're not going to have a force. Again, if it's not moving, there's no force. And so let me give you a harder problem. Let's say we have a magnetic field like this, and we have a charged particle, a positive particle that's moving up and to the left. And so how do you figure out where that magnetic force is going to be? Well, first of all, make your hand like this, and then you're going to point your index finger in the direction of that moving charge. So I'm moving it up and to the left. Then you want to make sure that your middle finger, that magnetic field, is pointed towards you, because you can see on this diagram that the field is coming towards us. And so once I've got that in order, my thumb is going to show me the magnetic force. And so that's going to go up and to the right. So that was pretty easy to solve. Let's go to another one. Now we've got a different...
I am going to stop here. Please take the time to watch this video. And he has another one right here. It's a continuation, which is Amperes Law. I haven't watched it, but just looking at the diagram that I have here, it looks like Amperes Law. Like I said, there are tons of video. There is another one here about how to determine... Oh, I like this guy, actually. He's one of my... His name is... he's European. Michel Van Biezen. He has really a lot of videos.
To fly a rocket ship, you need to be an optimist. No astronaut...
Welcome to
this guy. He's really good. I've been watching him for years. He has a bunch of videos that are really good. So there we go. He said magnetic forces and moving charges. I guess 6 of them, 6 videos, each of them about 8 minutes. He's very highly recommended. You don't have to, but this highly recommended. It is his channel. Anyway, okay, back to our class. I thought I'll just show you this very quickly before we move on. Where am I? Where is the book? There it is. Okay, let's move on now. Okay, so basically so if I have a charge, let me go back to our, so we have a charge Q, we have the velocity V, and let's assume that I have the magnetic field is into the page. Okay, you know what? I'm gonna draw this in a bigger place, in a wider place, because I want to have some stuff to write. Let's say I have a magnetic field like that. Okay, this is the magnetic field. That's into the page, correct? Remember, this is the back of the arrow into the page. That's the magnetic field. And let's assume I have a positive charge, and it's moving with velocity v this way. Okay, so when I use the right-hand rule, okay, again, I hope you will learn it. So it's going to be, okay, so the force on it is going to be equal to QV cross B. Okay, so in this case, it's going to be, I'm pausing, purposely pausing. I want to give you the chance to think about it. I hope you'll figure out it's going to be, should be up, right? V cross B should be up, right? Okay. I mean, you can't see my hand, but I'm using my hand to figure it out, okay? Anyway, so this is the charge Q, so that's how it works. Now, here is something interesting. If the charge is negative, you still use the right-hand rule, but whatever result you get for the force, you always make it opposite, okay? So for a negative charge, so this works for, so right-hand rule for positive charge. For a negative charge, you basically do the opposite. Whatever you get, whatever result you get, you just reverse it. If it's to the right, make it left. If it's up, make it down. If it's down, if it's out, make it in, and so on. Okay. Or another shorthand way to do it is the left-hand rule for a negative charge. But anyway, you can actually use the left hand; it will work out fine. But anyway, that's keep that in mind. Let me give you an example, and I have it right here from my notes. Okay, it says I have a proton, which makes it positive, right? I have a proton moves with velocity v equals to 8 times 10 to the 6 meter per second along the x-axis, along the x-axis. Then it enters a magnetic field of B equal 2.5 Tesla. That's a very large magnetic field. So it must be in some nuclear physics lab where they do an experiment. So they shoot the proton with a very large velocity, 8 million meter per second. And they do a heavy-duty experiment here. Then it enters a very intense magnetic field of 2.5 Tesla. Okay, it enters it at an angle of 60 degrees. Okay, to the x-axis, and he said, "What is the force on it?" Well, let me draw the diagram first, and then we'll talk about it. So here is, imagine you have a plane. All right, let's act like we are mathematicians. They always like to draw planes. Here's a plane, and here is your here is the x-axis, here is the y-axis, here is the z-axis, here is the proton right here, okay? And if it's moving in the direction, in the direction of the x-axis, right? That's what it says. Moves along the x-axis with this velocity. In other words, I can say that the velocity is equal to 8 times 10 to the 6 I, if I want to. Okay, you can do that. And then you have the magnetic field, however. Let me put it in a different color. As you can see, my ability to manipulate the stylus pen have improved a little bit. And what I'm now, I need to make a straight line. Good enough. Okay, this is the magnetic field right here. And this is the angle at 60 degrees. That's what it said. Let's read it again. He says it enters the magnetic field B of 2.5 Tesla at an angle of 60 degrees. That is the magnetic field at 60 degrees, not the proton. The proton is moving with velocity v along the x-axis. Okay. All right. Now he wants to find the force. Well, let's use the official rule. Says again, the vector version of it said the force is equal to, that is the force right here, right? For the proton, the Q becomes an E, so basically it's going to be E V cross B. Now, since numbers are given to us, let me convert this to a scalar form. So it becomes E V B sine theta, right? Why sine theta? Because it's a cross product. Remember we said A cross B is equal to what? A B sine theta. There's no vectors on A and B here. Vector sign on top of them. Why? Because they're scalars. You got that? So you can, there is a vector sign here, but not there. Okay. Okay, so it becomes that. So there we go. Just plug it in. It's really that simple. So charge of the electron 1.602 times 10 to the negative 19. Multiplied by the velocity is 8 times 10 to the 6 times the 2.5 Tesla times sine 60 degrees. Instead of saying the angle here is between what? V. See, you got V cross B, which means the angle here, guys, is the angle between B and V. Make sure that you know that. So this is V right here. And this is, excuse me, V. Did I say V? V and B. So the angle is right there, 60. You got that? Okay. And then we just calculate that. Simple. And when you do that, you end up with 2.77 times 10 to the negative 12 Newton. Very light force, but it is effective as far as the proton is concerned. Okay. He also asked, what is the acceleration of the proton? How do we do that? Well, that's easy, right? F equals ma, right? So A is equal to F over m. I have the force right here. 2.77 times 10 to the negative 12 divided by the mass. The mass of the proton is, what is it? 1.67 times 10 to the negative 27. And it's going to be a very large. Always acceleration of subatomic particles are very large. Anyway, so we have here 1.66 times 10 to the power of 15 meter per second. Got it? Okay. Moving on to the next topic, and that is, so far we have talked about two topics, Biot-Savart Law, and this interesting formula. And remember, this formula basically says, what is the force? Oh, let me mention one more thing about this formula. Sorry, I want to mention something very important about this formula. When you ask the question, how do we know, when we say, for example, the mass of the proton is 1.67 times 10 to the negative 27 kilogram. The mass of the electron, 9.11 times 10 to the negative 31 kilogram. How do we know those masses? How do we know this? How did we find out about them? I mean, obviously, we didn't take the proton, put it on a scale, and measure it, right? I mean, these numbers are extremely infinitesimal, really, really small numbers. How in the world did we know that? Okay, I'm going to show you how that goes. And there is a technique in physics and science in general. It's called mass spectroscopy. Mass spectroscopy. Okay, that's actually a really cool degree. You can't get a bachelor degree in spectroscopy, but it's by its own nature a graduate degree. Okay, I have a friend of mine who actually got a master's degree in spectroscopy, mass spectroscopy. And that is basically, it is the specialization where you specialize in finding masses of really tiny stuff. For example, a dust particle, a nanoparticle, a subatomic particle, atoms, ions, cations, whatever, anything really tiny. Even you can work in a forensic to find the mass of some really, really tiny particle for whatever reason. So, I mean, it's a big science. It's a big science that you can. So here's how they find it. This is interesting. Imagine you have two regions. Let's say this is a partition here. And let's say this region here, you have a magnetic field that is into the page like that, okay? Make sure you understand that, because I believe there is a homework problem related to it. I think. So there is a magnetic field, let's say it's into the page like that. So what I do, let's say I'm interested in finding the mass of, pick whatever you want, say a proton, okay? I don't know what the mass of the proton. I don't know this one. Okay, I want to find the mass, okay? So what I do, I have here at far away, I have what is called a proton gun, okay? What is a proton gun? It's basically a gun or a machine or an assembly that shoots protons. Well, how do I do that? Remember we did the capacitors? Imagine this is positive, this is negative, okay? And let's say I have a proton here, and then I'll let go. There is a large potential here, delta V, voltage, and I'll let go. So what's going to happen? The proton is going to shoot this way toward the negative plate, correct? Well, imagine that, you know what? Hold on. I'm going to make a hole here. So when the proton is attracted to the magnetic field, to the negative plates right here, it's going to go with very large speed, right? And it now is going to come out from here with very high velocity, right? Now I take this whole assembly and put it right here. There it is. Okay, and here is the proton coming out. Comes out with this large velocity. So now it's going to enter the field, into the magnetic field, correct? Well, let's use the right-hand rule. So as it enters the field, this is the velocity of it. I already know what the velocity is. I know that, okay? So what's going to happen to it is going to, remember magnetic field or particles in magnetic field, they always move in circular motion. So what's going to happen to it is going to go like that. And it's going to go in a circle, and there is right here a wall, which is basically a sensitive film, okay, photographic film, and so the proton is going to hit this spot right here. Okay, I've done this experiment back in my undergraduate days, and you do this whole assembly in the dark. Okay, the room is completely dark, and what you see, you actually see a spark here. You see a spark right there. And then, or in modern labs, you actually see the beam in a circular way like that. I think there is a picture of it in the book, but I can't locate it now. Give me a sec. Oh, it's right here. Figure. There's no figure number. That's weird, but the picture is there. Well, it's called under the section cyclotron motion. Anyway, let's continue. So now I know where the electron landed. Well, guess what? This circular path and the distance between the hole here and, let me put it in a different color. The distance between where the proton landed and where it came in, which basically the diameter of that circle. Okay, this is 2r. In other words, this is the radius r. Got it? Well, let's take the proton when it was here, let's say. Okay, so we have something like this. Here is the proton, and it's moving, let's say in this fashion. Well, there will be a force on it, centripetal force on it this way. Well, that centripetal force is nothing but the force QVB. You see what I'm saying? Sine theta, but theta here is 90 degrees, so it's 1. Okay? And that's equal to MA, but MA here, because it's circular, is centripetal acceleration, so that's mv squared over r, r being the radius. So I can find the radius by knowing where the proton landed. Okay? So with this in mind, so I can say that this is v right here, and this v cancel out, and I already know what the charge, so this EB equals mv over r, and therefore the mass is equal to EBR over v. Wow, there we go. I got the mass of the proton. And I know everything about it. See, I can measure the radius. Okay, I don't see the path here, but I see this one. I see where it landed, okay? And from knowing where it landed, I know this is 2r, because that's a circular path. Okay, so I know r, and then b, I already prepared the system, the whole assembly, to be at a certain Tesla, say 2.5 Tesla, for example. Okay, I already know what the charge of the electron, the proton is. And of course, with this assembly, I determine the voltage to know the voltage is, there is this relationship between voltage and kinetic energy, the one we studied. So I know what this velocity is as well. So from there, I can find the mass. The same thing applies for all the periodic table of the element, which is 105 elements. And we know the masses of every single one of them with their associated asymptotes. We're talking about 300 to 500 actually, well, that's probably 1,000 asymptotes. And we know the masses of all of them very accurately. Why? By using the technique of mass spectroscopy, which is this one here. You got it? Okay. That's one reason why this formula that we are studying is such an important formula in science. Okay. All right, another formula that is similar to it is this one. Oh, not this one, black. Okay. So imagine I have a wire, a current carrying wire, okay? And so there is a current going through it. So think of this current as a bunch of electrons, right? And they're moving with drift velocity inside, just like that. So if you take each electron by itself, it acts as if it is a charge moving with some velocity, and then there is a magnetic field. Let's assume there is a magnetic field on it like this. Let's say into the page. Okay, this is the magnetic field. Okay, so as the current is moving, what can happen? Well, the charges here, we're going to assume they're positive, by the way, okay? They apply to be positive. Assume that they are positive charges. As they move, well, there is a formula that said that there will be a force, a magnetic force on the wire. I'm talking on the body of the wire, okay? As a whole is equal to IL cross B. That's another formula. It's very equivalent to the formula we have just studied, Q equals V cross B. It's equivalent to it. Here, really for one particle moving with one velocity, V. Here you have a stream of particle, what we call the current, as you know. And then L here is really just the length of the wire. Okay? Just the length of the wire. You don't need to worry about the vectorial nature of it. You can just write it like this. The F equals ILB sine theta, if there is an angle between them. But that's basically what it is. Okay? So L here is the length of the wire. This is the current. That's the magnetic field. And then the angle between them, most of the time for our course is 90 degrees, so sine 90 is equal to 1. You see what I'm saying? Okay. So how do we use it? Well, one aspect of it, have you heard of the maglev train? You can look it up. Maglev train. The maglev, the magnetic levitation train. You know, have you heard of those trains that actually levitate above the ground? I'm going to talk about the magnetic flame in 1 second. Let me just do an example here for you. Here is an example. Again, I'm using my notes. It says a wire carries 30 amp current. The length of the wire is 12 centimeter. That's the length. There is a magnetic field at 60 degrees, and a value of B equals 0.9 Tesla. Question, what is the magnetic force on the wire? What is... Okay. So how do we do this problem? Okay, so let me draw a picture for you. Here is a magnetic field. The parallel lines, not like my lines. These are the magnetic field going in this direction. Okay, and then I have the wire that looks like that. Here it is. Cool. All right. And then you got the current going this way. Okay. And then the angle right here. Theta. You got it? Okay. And then, of course, here is the length. You know, pick a segment of it. It's given to us. There we go. Okay. So first of all, what's the direction of the force in this case? Well, it is ILB. You know, the force is I cross LB right there. So so it's going to be, the force in this case is going to be out of the, into the page, or rather, right? So the force here is going to be into the page. Okay. I mean, if I was in class, in regular class, we would have spent 15 minutes just training you guys how to use the right-hand rule. Unfortunately, we can't do that here. So you have to depend on yourself and learning how to find the direction of the force. Anyway, there it is. So so I want to calculate the force. So it's going to be ILB sine of theta, and that will be, just plug it in. So that's 30. L is 0.12. B is 0.9. And sine, what is it, 60. And then you get the answer of 2, if I did it correctly, 2.8, I think. 2.8 Newton. And there we go. That is the force on the wire. Another example very quickly, a little bit more complicated. It says, what do you have in here? I'm not going to write it down. Imagine I have a rectangular loop that looks like that. This is a rectangular loop. And there is a scale that measures the weight of the magnetic, the loop, excuse me, let's say a rectangular loop of wire, okay? And then there is a scale that measures the mass of it, or the weight of it, okay? So this is a balance. And the dimension of the loop is 10 centimeters by, it's not given to us, by what? It's unknown, probably not important. Okay, so this width is 10 centimeters. Then you have a current that goes through it like that. Current I, okay? And then only in the, says, a rectangular loop of wire hangs vertically in space, okay? So it hangs vertically in space where G equals 0. No, gravity is 0. B is shown perpendicular to the wire. Loop hangs from a balance which measures downward force. Okay, so here you have this region of the loop right there. You have a magnetic field. Not the whole loop, only this region. And it is out of the page. Okay, these dot means out of the page. Okay, so that's the magnetic field. Remember, the current going this way, right? It's a loop to go in this way and this way. Okay, and he says the force, the magnetic force, measured 3.48 times 10 to the negative 2 Newton. When wires, and the current in the wire, in the loop, is 0.245 amp. Okay, he said, what is the magnetic field? Okay, well, how does the, okay, let me show you. Imagine there is no magnetic field. Okay, so imagine just the loop of wire is there and there is a balance. Okay, so the balance in this case, and of course it's in zero gravity environment. So in this case, the balance is going to read 0. Make sense? There is no weight on it. There's no gravity. You get that? Now, while it's like that, I'm going to shine a magnetic field only on the lower half of the loop, as you can see here. Only on the lower half of the loop. Well, the question is, what would the magnetic field do to the loop? Well, it's going to impose a force on it. And, you know, there is an external magnetic field. Then there is a force associated. What is that force? Well, the force is given by that. Where the heck is it? Right here. You see what I'm saying? So there will be a force on it. So there should be a force. Whenever there is a magnetic field on a wire, so this force is going to be ILB, IL cross B, that is. Okay? What's the direction of this force? Again, we use the right-hand rule. Here is L. This is L right here. Right? And I is this way. And then B is out of the page. So if you calculate that with your right hand, I'm going to use my right hand rule now, and you're going to see that there is a force. Let me use the red color. The force is going to be this way. That's the magnetic field force. You see what I'm saying? This is the force. Use the right hand rule. Convince yourself that this is true. Remember, I don't think about negative charges. Just think of it like a positive charge. Or the current, the right-hand rule applies to it without flipping anything. You got it? So in this case, so I can, so that will be ILB sine theta. Of course, in this case, theta is 90, right? Everything is orthogonal. So in this case, just ILB. And, well, he gives us the force, is right here. And he gives us the current, and he gives us the length. Well, the length is right there. Oh, that's why he didn't give us this length, right? So it's just that. This is 10 centimeters. So in this case, it's going to be 3.48 times 10 to the negative 2 equals to 0.245 times the length, which is 0.1 meter, right? Times b. There we go. Then you can just solve for b. And b in this case will be equal to 1.42 Tesla. Okay? All right. Next, I have two more topics to talk about. Amperes Law. I think I can talk about it without looking at the notebook. All right. And then Amperes Law. Okay, let me just write for you the Amperes Law in its full glory. It basically says the line integral on a closed loop, this circle means closed loop, of B dot dl is equal to mu naught I. Okay, that's the proper way of writing it. I'm going to explain it to you in plain English, simple physics without this fancy stuff. Basically, what that means is the following. Imagine I have a wire. Okay, it's going upward. Current I. Hold on. Before I do that, remember the Biot-Savart Law. What does the Biot-Savart Law says? If I have a charge moving with some velocity, this charge, as long as it's moving, it is generating a magnetic field. In other words, when you ask a question, a general question, if somebody asks you, where does magnetic field come from? Well, it comes from moving charges. That's really what it is. Okay. So if you have a moving charge with some velocity v, there is a magnetic field associated with it equal to mu naught over 4 pi qv over r squared sine theta here, of course. There we go. All right, that's the Biot-Savart Law. Well, we have a similar analogous law, okay, and it's called Amperes Law. Here is how it's written properly, okay, in this formula. But I'm going to explain it to you in a simple way. If I have a current, see, this is the wire right here, and I have a current, there is an associated magnetic field to that current, and it is equal, it's going around like that. Use the right-hand rule. Again, Amperes Law. Maybe I should look it up for you. Hold on, let me look it up for you very quickly. Amperes Law. I don't think this law. I have it. Right-hand rule. Should be there somewhere. There we go. There's a bunch of them here. I never watched any of them. Let's try this one. This one looks fine, I think. Yeah.
This video is going to talk about the direction of calculating the direction for Amperes Law for magnetic fields and currents. A little bit of we need to have some loops is equal to I.
I just want to see his hand.
And we know that the charge that does that is the positive current. Backwards, you have to from right to left.
There we go.
My thumb is the current.
Look
so
at
I
that.
think about this as pointing my thumb in the direction of the current and grabbing this flow of charges with my right hand. My fingers are showing me the direction the loop turns. So there's my magnetic field, the B field.
The red
Let's
one.
look at an example.
Okay, the red one, the red. Go back. The red. See those red? The red circle here is the direction of the magnetic field, and this is the direction of the current. The current going this direction. See that? It's going. It's in the direction of the thumb. Okay. So basically, the curl of your fingers. See how your fingers is curling like that? That's the direction of the magnetic. Think of like the tip of your finger, index finger, is like a vector tip of a vector. So that's how it is.
So there's my magnetic field. What's the direction of the B field above this flow? So the issue here is how do I describe three-dimensional space on a two-dimensional screen? To do that, I need a little kind of notation. What I'm going to do is I'm going to put a dot on the screen. and the dot means I've got some kind of field action.
Oh, this is good enough. I have a. You can watch it yourself. Amperes Law. Anyway, there it is. Here's the guys. If you want to watch his, but anyway, I just found it at random, so nothing special here. All right, let me go back. So you got that. I hope you understand now how to find the magnetic field using the right-hand rule. Okay, so this is the direction of your thumb is this way, and that's the curl of your finger as you grab it. You see what I'm saying? As you grab the current, grab the wire, rather. Okay, and it's equal to. So if I want to calculate the intensity of this magnetic field, well, what is it equal to? Well, let's go back to this integral. Okay, so basically here it says the integral, the line integral, and this is the length of the loop, which is this loop right here. Okay, this loop around. Okay, remember this is a distance. The loop has a radius r, let's say. Okay, and so B dot dl basically is B. If B is constant, which is constant here and here, just like Gauss's law. So I can just say it is dl equals mu naught I. Well, this is nothing but the circumference of the loop, which is 2 pi r. Circumference of the circle times B equals mu naught I, and therefore B is equal to mu naught I over 2 pi r. Now, 99.9% of the problem that we're going to be dealing with, we're just going to have to use this formula, okay? We're not going to be using any fancy integrals there, okay? If you take a course in, if you're a physics major, you'll take a course in E&M, or rather, I mean, if you're an engineer, electrical engineer, I'm sure you're going to take an advanced course that you will be using Amperes Law for advanced stuff. But for this course, basically, you're going to be using this one, okay? So B is equal to mu naught I over 2 pi r. What does that mean? Well, again, let me give you an example quickly. So I have a current here. Here is current, let's say 2 amp, okay? I would like to know what is the intensity of the magnetic field here at a distance, say 1 meter. Let's make this 20 amp, okay? I want to know the magnetic field right there. Well, first of all, if I use the right-hand rule, what's the direction of the magnetic field at this point? Can you tell? It's into the page. Make sense? Here, however, it's out of the page. Okay. So basically it says B equals, here it is, mu naught I over 2 pi r. Plug it in. So mu naught is 4 pi times 10 to the negative 7 over 2 pi times I is equal to 20 amp over 1. So this gives me pi cancel out, 2 here, so it becomes 40 times 10 to the negative 7. See what I'm saying? Or 4 times 10 to the negative 6 Tesla. As you can see, it's small, but it's there. Here it is. You got it? Simple? Okay. Please read the cyclotron motion. It's on page 817. Nothing new. I have already talked about cyclotron motion. I didn't mention that it is basically the mass spectroscopy is the cyclotron motion. Please read that section because I believe there is at least one problem related to that. Also do example number 2911. Again, I've done this example. It has to do with mass spectroscopy. Cyclotron motion. It's not, that section is not named, but that's page 816. Okay, and then the cyclotron, and then you have some other sections. I want to make sure. You can ignore torque, guys. We're not going to cover torque. Okay, there is a section. Like I said, the chapter is huge. Okay, there's no way I could cover it within this 1 week span. So section 29.9 is about torque. We're not going to cover it, so you can skip that for this course. But of course, you are encouraged to read it. Honestly, you should be able to understand it without my help. And then what else? And then he goes on into section 29.10, magnetic properties of matter. You know, what is ferromagnetism? This is a very cool topic to learn about, ferromagnetism. why certain material is magnetic, like nickel and iron, some other not. In other words, when you say magnetic, I mean magnetizable. If something is magnetizable, we call it just a ferromagnetic. For example, iron is ferromagnetic, but say gold is not ferromagnetic, and so on. Okay, and the last topic that I want to talk about is the force between two wires, which basically it has to do with Amperes Law. Let me talk about it quickly. There is like one problem on that, but it is an important topic. It's not a section number, but it's under section magnetic forces and current. It's basically page 821, and it says force between two parallel wires. Force between two parallel wires. Unfortunately, I'm not going to derive it for you because it's a little bit lengthy. But basically, what it says is the following. If I have two wires, and they're both carrying two different, not necessarily the same current. They could be if they want to. And then let's say they're separated by a distance d. Okay? So this wire will produce a magnetic field going this way, correct? B1. And this wire is going to produce a magnetic field going this way, right? Okay? Because of those two magnetic fields, okay, they will generate an associated forces. Remember the force F1 is equal to ILB, is that right? And F2 is equal to I1 LB, and that's I2 LB, okay? Now, you can use those to derive the force law, which I'm not going to do here, but basically you'll end up that it's a force between them, okay? Because they are going in the same direction, the force between them is going to be attractive. In other words, you will see that both forces are attracted to each other. And this force is equal to mu naught over 2 pi, okay, I1, I2 over d, the distance between them, multiplied by the length of each wire, assuming both of them have the same length. You got that? Okay, they both have the same length, L. You got it? Okay. I'm trying to find an example for you. Hold on. I have it in my notes here. Just give me a sec, please. I remember I had a bunch of them in the back of the notes. Find the magnetic field. And I'm sorry for that taking so long. I'm trying to find a good one. You know, I've seen so many of them, and now I can't find any. Okay, that is one. Sorry. I think this is a good one. Okay. Oh, and then, of course, if the two wires are moving, the current are moving in opposite direction, you still have the same expression, except that if they're in opposite direction, then the force becomes repulsive. You got that? So if I have one current going this way, and this current going down this way, then the force is repulsive. You got it? Okay. Let me do one example, show you how this works. Imagine I'm going to take this one. That's just from my notes, guys. I have a current I going this way, okay? Then I have a loop of wire going this way. And there is a current going through it like that. We're going to call that I2, okay? This I1 is equal to 5 amp. I2 is equal to 10 amp. The distance between this side of the wire to this wire is C, and the width of the wire is A, and the length is L. These numbers are given to us. I'll give them to you in a sec. Such that A is equal to 0.15 meter, C is 0.1 meter, L is 0.45 meter. The question is, find magnitude and direction, mag and dir, of the net force exerted on the rectangle. This is a good problem, now I remember it. On the rectangle by the magnetic field of the straight wire. Straight wire. Okay? You can pause the video and think about it for a sec before you, continue. But anyway, here's how we work on it. Oh, I don't have the solution. All right, live dangerously. We'll just do it without my my solution in front of me. Okay, so what he wants, I want to know the force, the net force between this whole thing. Now, you agree with me. We said that the force, let's talk about I1. Remember, this I1 going this way. Then you have I2, this I2 going this way. And then I2 also is going down here. This is I2 as well, right? So let me look at the force between this side of the wire right here. Whoop, what happened here? What is that doing that? There we go. So this side of the wire and I2, this side, let's call it side, nothing. Okay. So because they're both going in the same direction, so that means the force between them is attractive. You agree with me on that? However, between this wire here and this segment is going to be opposite direction, so it's going to be repulsive. So let's do the attractive first. So we said that the force between them is going to be, if you remember, mu naught over 2 pi I1, this is the formula, over d L. L being the length. The length, what is L right here? Okay, so let's do this one. Call that F. We'll call it F1. I don't like 1. What do I call that? Let me call it F prime. How about that? Okay, and then this one is F double prime. Okay, whatever, but it's not the derivative or anything. Okay, let's calculate that. So mu naught, which is 4 pi times 10 to the negative 7 over 2 pi. And remember, look at the direction of it. It's to the left, so that makes it a negative, right? I forgot to mention that. I1, I2, so that's going to be 5 times 10, right? Divided by the distance between them, which is C, and that's equal to 0.1, times the length, which is this one, and that's equal to 0.45. There we go. Now we just calculate that. Let me use my calculator very quickly, and please use yours. Maybe I'll just get you get a wrong answer. Of course, before I do that, the pi's cancel out, so I end up with 2 here. 2 times 10 to the negative 7, so 2 negative 7 times 50 times 0.45 divided by 0.1. Answer. If I did it correctly, it's going to be 4.5 times 10 to the power of, it's too dark in here, negative 5 Newton. Got it? Okay, so this force, F prime, is equal to this number. Great. Let's do F double prime, which basically F double, can I do it in different color? It's probably easier. So now they're going to be the force, oops, sorry, not this one. It's going to be a repulsive force. There's going to be this way, F double prime, and this one here, this segment. You see what I'm saying? I forgot to mention the force, there's no force here, it's 0, right? The force here is 0. You agree with me on that? And the force here is 0, because they are parallel, perpendicular. All right, so I want to calculate this force here. So that's going to be positive, and it's going to be basically the same exact formula. So let's just plug it in very quickly. So it's going to be, using this one, that's nothing but 2 times 10 to the negative 7 times 5 times 10 times 0.45 divided by what? It divided by A plus C, correct? Is that right, guys? So A plus C. So that's going to be 0.25. And it's positive, right? So the answer to this, let's do it. So 2 negative 7 times 50 times 0.45 divided by 0.25, answer 1.8 times 10 to the negative 5, and that's positive, right? So what is the net? Well, just add them up together. 1.5 minus 4.5, 10 to the negative 5, that will be 1.8, that is, minus 4.5, that will be negative 2.7 times 10 to the negative 5 Newton. That's the net force. You see what I'm saying? Now, one more thing about this. Let me just make this, and then we'll end the video. Let me draw it again. So what we have in here, you get this wire like that, and here's the loop of wire that we were talking about, right? So you have this force going this way, and this force going this way. Notice that this force here is 4.5, and this force is 1.8, which means this force is stronger. Obviously, why? Because it's closer, right? But what that means, if you're actually doing this in real life, in a lab, this side of the wire is going to bulge a lot like this. Let me put it in red, maybe. It's going to bulge like that. I'm exaggerating the way it looks. Where this is also going to bulge, but in a lighter way, smaller. So this is going to be a big bulge like that because the force is 4.5, and this one is 1.8. You got it? Okay. I think I'm going to end here. Let me know if you have, when you work on the homework problems, let me know if you have any questions, okay? And we'll stop here. Have a great week. Bye-bye.